Democritus is the first philosopher who tried to answer the idea or the question, what makes up everything. He coined the term atomos, which means cannot be cut, or the other name for cannot be cut or atomos is the word indivisible. Indivisible. So when we say atom is indivisible, it means cannot be cut or cannot be divided anymore, because that's the smallest you can get. And he said that these atomos are made of a single material that is formed into different shapes and sizes. That's why you see different types of things around you, because atoms are of different shapes and sizes. But then, at 300 BC, early to 1800s, there was another philosopher. But this time, this philosopher, in the name of Aristotle, was very influential. He was very popular and people believed him. So, Aristotle made another philosophy. He said that all matter is just made up of 4 elements: fire, air, water, and earth. And that matter has 4 properties only: hot, cold, dry, and wet. So with this idea, people believed him. For 2,000 years, 2,000 years, people believed his idea. Remember how influential he is. So Democritus was forgotten. But then, in 1800s, the advent of science, modernization of science, came a person named John Dalton. So Dalton postulated what we call the modern atomic theory. So in the modern atomic theory of Dalton, he resurrected the idea of Democritus. So if you look at the illustration of the two, it's the same. Dalton perceived the atom to be indivisible as well, still indivisible. And it's a tiny sphere. And that's why he said that atoms are uncuttable or cannot be divided. And he said that atoms of the same element are exactly alike. They're always identical. And he was able to support this with evidences. But then we jump to the current one right now. These two things are already wrong. These are already disproven. Because right now we know that there are things inside the atom which we call the subatomic particles. Your protons, electrons, and neutrons. So therefore, this is incorrect. And then the second one, this second statement of Dalton is also incorrect nowadays, because even if the atoms are identical, they can be different in some ways. Just like an identical twin. An identical twin may look exactly the same, but we know that there are also differences between these two persons. So that's the same with atoms. Even if they're the same element, they are not exactly alike. And I will discuss this by tomorrow, the reason why this is incorrect. But for now, let's attribute Dalton for all his contributions to the modern atomic theory. That means he was able to let the people be aware that, hey, don't believe Aristotle, we're now going to believe in the scientific evidence that we are providing you. Okay? After Dalton, there comes another person who further discovered something else. Remember that Dalton said atoms are uncuttable. J.J. Thomson, the next one after him, in the early 1900s said, uh-oh, Dalton, you are incorrect. There's something inside the atom. And J.J. Thomson said, I was able to discover something inside the atom, and it is negative. And these negative particles are what we call the electrons. J.J. Thomson discovered the negative electrons in the atom. And we call his model the plum pudding model. Let me underline that. It's the plum pudding model. Or in the modern world, we call it the chocolate chip cookie model here. But during his time, J.J. was into pudding. His favorite was a pudding, and in the pudding there are plums embedded in the bread. So this is how he visualized the atom. From a sphere of Dalton, he said, there's something inside, and I put my negative here. This is where he placed his negative, just like the plums or the chocolate chips in the cookie. And then the people are asking him, where's the positive, Thomson? If there's a negative, there should be a positive. So, because Thomson was limited, he was making up something. So he said, okay, let me think about it. Okay, I know. So he was making up something. The atom, the whole atom, is positive. Then the negative electrons I discovered are embedded in it. So that's why the illustration of Thomson's model looks like this. And we know that this is incorrect. But his greatest contribution is these negatively charged particles inside the atom, and we call them electrons. Okay? So that was his greatest contribution. So, of course, it doesn't end there, because he made up this structure here, which is not proven with many evidences, right? So here comes another friend of his. His name is Rutherford. I'm sorry for that. Rutherford. Ernest Rutherford in early 1900s also. So Ernest Rutherford did an experiment. So let me show you what he did in his experiment. So Rutherford did an experiment which we call the Rutherford's gold foil experiment. Okay? So this person, Rutherford, helped his friend Thomson to better his image of the atom. So what did he did in this gold foil experiment? So he had this radioactive source machine that emits a beam of alpha particles. This is alpha. So positive alpha particles. So this beam is strike on a gold foil here. So this is the gold foil. I don't know if you can see it, but this gold foil is very thin, and they put it in place so that the alpha particles will readily strike on it. Then the gold foil is surrounded by a detector, the detector of these alpha particles. So when he did this experiment, he noticed something. He noticed, first observation, most alpha particles travel through the foil undeflected. Meaning undeflected, it went through straight on the foil. It went through straight, no obstruction. Second observation, some alpha particles are deflected or bent by small angles. Look at this. There are two, and the third arrow here, they have bent a little bit, and there's only a few of them. So this is the second observation. The third observation is, it says, occasionally an alpha particle travels back from the foil. You see this arrow here? This is the one that went back. Why is it that there's a rare occasion of this and the bending? And why is it that majority pass through undeflected? So now here are the interpretations of of Rutherford's theory. His first interpretation is the reason why most alpha particles went through straight is that the atom is actually mostly empty space. There's nothing in the atom mostly. It's vacant. It's empty. So therefore, if you look at J.J. Thomson's atom, it's full. So J.J. Thomson is wrong. This is wrong because Rutherford proves it that, hey, most of the atom is empty space. And then the second and the third, what? Why is it that there is some bending? Remember, the charge of your alpha is positive. If there's bending, it means it strikes another positive region. And so, this is the crucial discovery of Rutherford. He discovered the nucleus. The nucleus is a positively charged space or region in the atom. And he said that this is a very small region in the atom, and it's located in the middle of the atom. So Rutherford's Goldfall experiment is also called the nuclear model of the atom, because he discovered the nucleus, and he said that the nucleus is positively charged. Okay? And the third one, he said that because this nucleus is dense and it can even return back a particle sometimes, then the mass of the atom is mostly in the middle, which is in the nucleus. So the atom's mass is concentrated in the middle, which is the nucleus, which relates to what we talked about last week about mass number. The mass number is equal to protons plus neutrons. And protons and neutrons are both squeezed in the nucleus. They're both squeezed in the nucleus, so therefore they are the cause why there is atom's mass. Okay? So Rutherford made a great contribution of clearing out the image of an atom. So if you go to his illustration of the atom, if you look at this, so he said that my friend JJ is still correct. There is still negative electrons, but the negative is outside the nucleus that he discovered. So that is what the contribution of Ernest Rutherford is. Take note that Ernest Rutherford did not discover the protons and the neutrons. He discovered the nucleus. It's a space, it's a region that's positive, and it is a tiny, dense region in the middle of the atom. Then later on, there were other scientists who discovered the protons and the neutrons. Okay? But Rutherford discovered only the nucleus. But then it's not enough. There was a question to Rutherford. Okay, Rutherford, you discovered the nucleus. How about the electrons outside? Can you tell us how the electrons are moving outside the nucleus? Rutherford couldn't answer.
Yes, sir.
Oh, yeah. He couldn't answer, Devin. But then, yeah, you're right. There was a scientist after him who attempted to answer it in the name of, here, Bohr. Niels Bohr in 1913. So Niels Bohr attempted to explain how the electrons are arranged outside the nucleus of the atom. Then what did he say? The electrons are arranged like the planets in the solar system. He said that each electron has an orbit. circular orbit, and it has a specific orbit to follow. And that's what he said. That's why the name of Bohr's model is sometimes called the planetary model of the atom. So planetary, planets in the solar system. But there was a problem with him. Bohr couldn't explain atoms that are big, atoms that have plenty of electrons. He couldn't explain that. He's limited to very small elements like hydrogen and helium, because he backed this up mathematically. He had an experiment and he had a very complicated math equation to support this. But he couldn't justify big atoms anymore. So that means this is lacking. So here comes a group of people: Einstein, we have Erwin Schrödinger, Werner Heisenberg, and all these people in the quantum physics field. They furthered the discovery of Bohr, made a lot of experiments, and then they had computer simulations already. And they were able to find out that this idea of Bohr, that electrons have fixed orbits, that's wrong. That's wrong. Electrons are now moving at a certain space again, which they call the electron cloud. So this is now the electron cloud model. And this is the current model that science is teaching you. And next week I am going to dig deeper with this, and I will tell you more about the electron cloud model. So there might be a question on your mind, and why is it, Miss Narca, that last week we draw the atoms to be like this using Bohr's model? Okay, the electron cloud model is very complicated. Like, you cannot draw it simply. Okay? So we still adopt the representation of the arrangement of the electrons using Bohr's model, but it doesn't mean that's the actual thing. We're just making sure that we can represent it clearly, how many electrons per energy level, but in reality, it's much more complicated than that, which I'm going to tell you by next week. But for simplicity, chemistry still adopts the pictorial representation of Bohr, with some explanations though. Okay? But right now, the modern theory that we believe and that the scientific community is accepting is the electron cloud model. Okay? Now this ends our discussion for the atomic models.